Now the next periodic property or the periodicity is that is ionization enthalpy. Now what is ionization enthalpy? Ionization enthalpy, the term have the enthalpy word. Enthalpy means it is a somewhere here we are talking about the energy. Enthalpy means it tells us about the amount of energy absorbed or evolved at constant pressure. So here somewhere we are talking about the energy. Now what is enthalpy? Ionization enthalpy. Then simply I can say that it is the energy required to remove an electron from an isolated gaseous atom in its ground state. So here we are something talking about the removal of the electron. Now the electron which is up here, I just wanted to remove an electron from the outermost shell of an atom in a gaseous state. So whenever ionization enthalpy, we measure the atom should be in a gaseous state, and here we consider the gaseous state only for the comparison purpose, so that whenever we have to compare the ionization enthalpy of the different atom, then comparison can be done easily. So suppose I have an atom. This is an atom. This is the nucleus of the atom, and let there is an electron present in it. Now I know that the nucleus have the positive charge because of the presence of proton, and the electron carry the negative charge. So ultimately there is some attraction, electrostatic attraction between the nucleus and between the electron. Now here I just wanted to remove this electron from the outermost shell. I just want to remove it. Now for the removal of an electron, since there is an attraction between the nucleus and electron, the nucleus is holding the electron. That's why the removal of the electron is not possible easily. So first, to remove the electron from the outermost shell, we have to first break this force of attraction present between the nucleus and between the electron. So first here the required thing is that breaking of this attraction. An attraction can be broken only after applying or after supplying some amount of energy. So here what we do, we just supply some amount of energy, electron gains those energy, and after absorbing energy, it breaks that attraction and it comes out of the outermost shell. And to come out of the shell, whatever the energy is absorbed by the electron, that energy is called as a ionization enthalpy. So it is an energy required to remove an electron from an isolated gaseous atom in its ground state. Okay, now to remove the electron from the outermost shell, how much energy will be needed? It totally depends upon the attraction which is present between the nucleus and between the outermost shell. If the attraction is weak, I will say simply the lesser amount will be needed, and hence the ionization enthalpy will be low. But if the attraction is strong, then to break that attraction, more amount of energy is required, and hence the ionization enthalpy will be high. So whether less amount of energy, whether the ionization enthalpy will be low or ionization enthalpy will be high, it totally depends upon the attraction which is present between the nucleus and between the electron. So as I said, it totally depends upon the attraction. So higher the attraction, more the energy will require. Lower the attraction, lesser the energy will require, means the ionization enthalpy will be low. So for example, suppose this is an element M. Here I am just removing one electron. After removing one electron, what will happen? It will get converted into M plus. One electron is lost. So one electron is lost. So during this process, as I said, some amount of energy will be required to remove electron, and whatever the energy is required is called as ionization enthalpy, that is delta H. Ionization enthalpy, it is either represented by I between delta and H, or sometimes we use the term IE also. So whatever the energy will be needed, whatever the energy is absorbed is enthalpy. Enthalpy represents the amount of heat absorbed as well as evolved. It is represented by the sign positive or negative. If the heat is absorbed, the sign will be positive for the delta H, and if heat is evolved, then the sign is going to be a negative. And ionization enthalpy, since it is the amount of heat absorbed, therefore delta H is always positive. That means ionization enthalpy is always positive. Okay. Now let's talk about whether what happens to the ionization enthalpy when we move from left to right, that is across the periodic table. Or let's see what are the different factors which affect the ionization enthalpy. Okay, so before that, see, if I'm removing the first electron from this, then I can say that whatever the energy is required, it is called as first ionization enthalpy. It is also known as first ionization enthalpy. That is first ionization enthalpy, that is energy required to remove an electron from a gaseous atom in its ground state. So when one electron is removed, we always remove one electron from the gaseous state. Now suppose there is a 2 electron present in the outermost shell and I wanted to remove second electron also. First this electron is removed and I just wanted to remove this second electron. Now the question arises, for removing a second electron, whether more amount of energy will be needed compared to the first one or less, or the same amount of energy is required. Then answer is that if you want to remove the second electron, then energy required is always more than the first one. It is always more. The reason, because the first nucleus was holding both the atoms. It was holding both the first nucleus was attracting both the electron. But once so whatever the power of nucleus we have, it was distributed on both the electron. But suppose once you remove this one electron, after removing of this one electron, whole energy of the nucleus get concentrated on the first one. And since it get concentrated on the, after removing the first electron, the whole energy of the nucleus, whole power of the nucleus get concentrated on the second electron. So now, after removing a first electron, the second electron is tightly held by the nucleus, and that's why the more amount of energy is required to remove that electron from the outermost shell. So now here, so whenever you want to remove the second electron is never come from the atom. If you want to remove the second electron, means already one electron has been removed. So for removing second electron will be removed from M plus only. So I'm removing one more electron, so it will now carry plus 2 charge plus electron, and this is delta IH, that is second ionization enthalpy, or it will be represented by IE2. And as I said, the second ionization enthalpy is always greater than the first ionization enthalpy. It is always higher than first ionization enthalpy. So let's see the example for this, for the second ionization enthalpy and the first ionization enthalpy, that how the energy means for which the energy is more or less. For example, suppose I want to, let's take the example of calcium. Suppose from calcium I remove the first electron. Calcium which have the electronic configuration 2882, that is having 2 electrons in the outermost orbit. So I'm removing the first electron. So here after removing a first electron, I just measure the delta H value and I come to know that this value is 590 kilojoules per mole. Now suppose one electron is removed. Now I wanted to remove the second electron. This is a value kilojoules per mole. So for removing the second electron will be come out from the calcium plus. So calcium plus, it will become now, after losing one more electron, it will become calcium 2 plus 1 electron. And when I measure the second ionization enthalpy, the value is approximately 1050 kilojoules per mole. That means from this data, I can say that the energy required for the first electron, that is first ionization enthalpy, is always less than second ionization enthalpy. Suppose if the outermost shell contains third electron, if there is a third electron, then for removing that third electron, still the more amount of, that means in that case the highest energy will require to remove the third electron, then second, and then first electron will require the lowest energy. So here I can say the ionization enthalpy for second electron is more than ionization enthalpy for first electron. So this is about the first and second ionization enthalpy. Now let's see the different factors which affect the ionization enthalpy, how the ionization enthalpy changes when we move across the periodic table. Okay, So the factors affecting the ionization enthalpy. So the factors which affect, the first factor which affect, all those factors which is going to affect the the attraction between the nucleus and the outermost shell will affect the ionization enthalpy also. The first factor which affect is nuclear charge. And in atomic radius, while studying the atomic radius, I already told that whenever I'm using a word nuclear charge, you have to just think that we are moving from left to right in a periodic table, because nuclear charge effect is applicable only when we are moving from left to right. So when we move from left to right in a periodic table, I know that the nuclear charge goes on increasing. What is nuclear charge? It is a charge on the nucleus due to the presence of proton, and how much protons the nucleus will have, it is decided by the atomic number. So when we move in a periodic table from left to right, the atomic number continuously increases, and atomic number increases means protons increases. Proton increases, it means nuclear charge will increase. And since the nuclear charge increases, means the nucleus is pulling more and more to the electron. That is, the attraction between nucleus and electron increases. And if the attraction between the nucleus and electron is increasing, it means the removal of the electron will become difficult. And hence I can say that more energy will require to remove the electron from the outermost shell. So as the nuclear charge increases, the attraction increases. Attraction increases means the energy required for removing electron also increases. So here I can say that when we move from left to right, nuclear charge increases, and hence ionization enthalpy also increases. Enthalpy also increases when we move from left to right in a periodic table. So here, simply, I can say that the nuclear ionization enthalpy is directly proportional to the nuclear charge. More the nuclear charge, more the energy required to remove an electron from the outermost shell. The second factor which affect the ionization enthalpy is number of shells. And whenever we use a word number of shells, the number of shells means we have to move from top to bottom, because the number of shells changes only when we move from top to bottom. So when we move from top to bottom, the number of shells continuously goes on increasing. As it is written that number of shell increases from top to bottom, it increases 1 shell, 2 shell, 3 shell, like that. And if the number of shell is increasing, means the atomic radius increases. Atomic radius means the size of atom increases. And if the size of atom is increasing, it means the outermost shell electrons are moving away from the nucleus. And if the outermost shell electron is moving away from the nucleus, it means the attraction between the nucleus and electron decreases. And if the electron gets weaker, that means the less energy will require to remove the electron from the outermost shell. The nucleus, electrons is getting away from the nucleus. The reason, because the shells increases. So attraction between the nucleus and electron decreases. So less amount of energy is required. And hence less energy means the ionization enthalpy decreases. So when we move from top to bottom, number of shell increases, radius increases, that is size. So attraction gets weaker, and attraction gets weaker. That's why I can say that less energy is required to remove the electron. That is, ionization enthalpy also decreases. So here, from top to bottom, here I can say the ionization enthalpy, in a simple word, that it is inversely proportional to the number of shells. More the shells, bigger the size of an atom, weaker will be the attraction between nucleus and electron, so less the energy will require to remove the electron. That is, ionization enthalpy will be low. Then third one, the third factor which affect the ionization enthalpy, that is shielding effect. Now what is shielding effect? Then shielding effect, we had already learned about the shielding effect also. That shielding effect, it is a repulsion produced by the inner shell electron to the outermost shell electron. If it is in a multi-electron atom having a more than one shells, then the electron present in an outer inner shell always produces a repulsion to the outermost shell electron because of the same charge. So suppose there is a nucleus is attracting this electron. This electron is from the outermost shell. There is a inner shells also. So this nucleus is attracting this electron, but at the same time the electron which is present in outermost shell, because of the same charge, they repel this electron. And due to that repulsion, what happened? The net or effective shielding effect decreases. Effective nuclear or the nuclear charge decreases. And due to that decrease in a nuclear charge, or due to this nuclear charge decreases, means the attraction also decreases. And attraction decreases means simply I can say that less energy will require to remove the electron. So the shielding effect, due to the shielding effect, this electron get repulsion from the inner shell electron. Due to repulsion, the attraction between the nucleus and electron decreases, and due to that decrease in attraction, I can say less energy will require. And shielding effect goes on increasing when we move from top to bottom, and hence the shielding effect increases, that is attraction gets weaker and weaker, and due to which I can say ionization enthalpy also decreases. So here I can say that ionization enthalpy is inversely proportional to shielding effect. More the shielding effect, more will be the repulsion by the inner shell electron, and hence weaker will be the attraction and less the energy will require to remove electron. Then point number 4, that fourth factor which affect the ionization enthalpy. It is a penetration power of electron. The fourth effect, it is a penetration power of electron. Now what is that penetration power of electron? See, it has been observed that if there is a more number of electron in the outermost shell, there are 7-8 electrons in the outermost shell. In that case, the electrons will be present in s orbital, p orbital also, and if I wanted to remove the electron from d or f orbital, then it has been observed that the energy required for removing electron from the s orbital of the outermost shell is more than p, than d, and then f. Means if the electron present in a s orbital, if you wanted to remove an electron from the s orbital, then more amount of energy is required to remove it from compared to the p or d or f orbital. Now suppose there is a 4 electron means 2 electrons will be in a s orbital and the 2 will be in a p orbital. In that case, which electron will require more energy? Then it has been observed that the electron which is the s orbital electrons are having a more penetration power, and if s orbital is having a more penetration power, means the electron present in s orbital will be more closer to the nucleus, and if the electron present in a s orbital will be more closer to nucleus, means will be tightly held by the nucleus, and hence more energy will be required to remove the electron, that is ionization enthalpy will be high. But if the electron present in a p orbital, then compared to s orbital, the p orbital have a lower penetration power. Lower penetration power means it will be away from the compared to s orbital, it will be away from the nucleus, and hence the attraction between the s nucleus and p orbital will be weak. And if the attraction is weak, then in that case I can say the less energy will require to remove the electron. While I said the attraction between the nucleus and the s orbital electron is more, and that's why more energy will be needed. This attraction is more because s orbital is having a high penetration power, and due to which it is more closer to the nucleus, that's why more energy is needed. And that's why the electron present in a same outermost shell, the electron present in a s orbital is require more energy compared to the p, d, and f orbital. That is, ionization energy for s orbital is more. Then next is the next factor, that is fifth factor, electronic arrangement. Electronic arrangement, that is arrange, or I can write the electronic configuration, how the electrons are present in the outermost orbit. See, we all had heard about the stability of the atom, and that stability is either because of the complete octet in the outermost orbit, but in many cases the outermost orbit is doesn't contain 8 electron. Or I can say we had heard about the half-filled and completely filled stability. I know that if there is an electron present in a half-filled, if the orbital is a half-filled or completely filled, half-filled or completely filled, then in that case the removal of the electron will be very much difficult from the removal of electron will be very much difficult, and the ionization enthalpy will be more. For example, suppose there is an atom having outermost shell configuration p3. If it is having a p3 configuration, means the p orbital will have 3 electrons, and if the p orbital contains 3 electrons, it means it is highly stable. And if it is a highly stable, due to the half-filled configuration, it is having a stability. So in that case, if you wanted to remove this one electron, then after the removal of electron, it will become p2. And so after the removal of electron, what is happening? It is losing its stability. So this atom which is having a p3 configuration, it completely tried not to lose this one electron, because after losing this one electron, it will become unstable. So it's a completely tries not to lose, and that's why it requires a little bit more amount of energy for or it will require, or hence the electron will require more energy to come out, as it is affecting the stability of an atom. This happens with the p3 configuration, this happens with the p6 configuration, this happens with the s2 configuration. If s orbital is also completely filled, that in that case also the removal of electron will be difficult. Or it happens with the d5, d10, means half-filled and completely filled stability. We will see some examples based on this, that is on electronic arrangement. If after the removal of electron, if an atom is losing its stability, then in such cases it doesn't lose, it requires a very large amount of energy to remove the electron compared to the expected energy. So this is about the ionization energy that is required to remove the electron from the outermost shell of an isolated gaseous atom in its ground state. As I said, how much energy will require, it totally depends on attraction. The energy required, suppose if you wanted to remove the 2 electron, then energy required for removing second electron will be always more than first. First electron is always removed from the atom, but the second electron is always removed from an cation. So if someone is asking what is first ionization enthalpy, then I will say it is the energy required to remove an electron from an atom. But if it is asked that what is second ionization enthalpy, then my answer will be that it is energy required to remove an electron from a monovalent ion, because we are removing the second electron from monovalent ion. Okay. Here I had explained the things with the help of example and the values. Then we have different factors which affect the ionization enthalpy. All those factors, as I said, which affect the attraction between the nucleus and electron will affect ionization enthalpy also. That is, the factors are somewhere common. The factors affecting the ionization enthalpy is somewhere common with the atomic radius. Nuclear charge, ionization enthalpy is directly means the more the nuclear charge, more stronger will be the attraction, more will be energy. Then ionization energy inversely proportional to number of shell, because as the shell increases, the attraction goes on become weaker. Shielding effect inversely proportional, because shielding effect, that is a repulsion produced by the inner shell, or again weaken this force of attraction present between the nucleus and electron, that is less energy will be needed then. And penetration power, as I said, the electron present in the outermost shell, if an atom is having the multi number of electron in the outermost shell, then electron present in s orbital will require more energy to come out than p, d and f orbitals. And then electronic arrangement, where I'm talking about the stability of an atom, that if an atom is having completely filled or half filled configuration, then again removal of electron will be difficult. That means more energy will be needed to remove the electron. Here one more thing, that ionization energy is inversely proportional to atomic radius. That means higher the atomic radius, lesser will be the energy required to remove the electron. Higher the atomic radius, it means If the atom is a bigger, the attraction will be weak and hence the less energy will be needed. So from left to right, you can see that atomic radius decreases, but at the same time ionization enthalpy increases. Here from top to bottom, shells increases, shielding effect increases, and hence the ionization energy decreases. So from top to bottom, ionization enthalpy as I said, it decreases. Again, here also shows the inverse relation. Atomic radius increases while ionization enthalpy decreases when we move from top to bottom. Now let's see the ionization enthalpy value of the same element. That is, here as I said in the periodic table, that is in periodic table I said that from left to right the ionization enthalpy goes on increasing, while from top to bottom this value goes on decreasing. Now in the case of periodic table, now here I had written the ionization enthalpy of the certain element. Now lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, these all are the element which is present in a second period, and they all are present in a second period means I am moving from left to right. And if I am moving from left to right, then rule says that the value should goes on increasing. Now let's see whether the value is continuously, gradually it is increasing, or we are getting some problem in between. 520, it becomes 900. It is correct. But from 900 it becomes 800. Now here we are getting some problem. That is, from 900 the value should be greater than 900. This boron should be greater than 900, but here the ionization enthalpy is for the boron is less than beryllium. Now question arises that why this is happening. Let's see what happens over here. The same, then here from 800 it becomes 1086, increases. 1402 increases, again it decreases, means again the second problem is here. And then fluorine and then neon, it is increasing. Now what will be the main reason that we are getting such type of thing, that is from beryllium and boron, between beryllium and boron, why the value decreases? Then the answer can be given on the basis of its electronic configuration. If I am writing the electronic configuration of the beryllium whose atomic number is 4, so its configuration is going to be 1s2 2s2. 1s2 2s2 means the electron is present in the 2s orbital. And if you wanted to remove, and for the boron, let's see boron also, configuration is 1s2 2s2 to p1. This is the third electron, sorry, fifth electron, that is it moves to the p orbital. So if you wanted to remove the outermost electron from here, that outermost electron, that is a fourth electron, and fourth electron is nothing but this electron. So I wanted to ultimately remove this electron. The removal of this electron will be difficult in this case because this electron, we are having S2 configuration, that is completely filled s orbital, which is stable. We saw that the fifth factor which affect the ionization enthalpy was the electronic arrangement. And in that part I said that if an atom is having the stable electronic configuration, half filled or completely filled stable configuration, in that case the removal of electron require more amount of energy. So the 2s2 configuration means it is a stable configuration, so here the removal of electron will be more. For example, suppose this was 520, so this value will be somewhere 700 or something. For beryllium, somewhere it requires 700 kilojoules of energy to remove the electron, but due to the stability, since the stability problem is, since after removing electron it will lose its stability, that's why it does not loses its electron easily, and that's the reason that we have to supply more amount of energy. And how much more energy? Approximately 200, and that's why the value becomes 900. That means stability, due to the stability, it requires certain amount of more energy, and hence the value becomes more than boron. In the case of boron, the removal of this electron, the outermost electron, if you wanted to remove, boron atomic number is 5. So if you want to remove the outermost electron, means you have to remove this electron. And if you are removing, P1 is not the stable configuration. So if you are removing this electron, it doesn't have any problem with respect to the removal of electron. It will easily lose the electron, and that's why it requires only 800 kilojoules of energy. But this requires 900 kilojoules of energy because after removing that electron, it will lose its stability. So, and every atom tried that they should not lose its stability, and that's why the more energy is needed. Now, in the case of nitrogen and oxygen, what happens? The rule says that oxygen should have the more ionization energy compared to the nitrogen, but here the thing is totally different. Here we are having oxygen is having less energy and the nitrogen is having more energy. The reason, again, I can say somewhere with respect to the stability also, stability only. Let's see what is the reason. Nitrogen, atomic number is 7 and its electronic configuration is 1s2, 2s2 and 2p3, having 3 electrons in the outermost orbit. Having 3 electrons in the outermost orbit. Now, after the nitrogen, the next is oxygen. Atomic number for oxygen is 8. Configuration is 1s2, 2s2, 2p4. So 4 electrons in the outermost orbit. First, all the electrons will enter singly and then pairing. So if you wanted to remove the electron, the 7th outermost electron, the last electron from the nitrogen, then removal of that last electron, that means this will be the removal of this electron will be removed. And if this electron is removed, then again nitrogen will try not to lose this electron, because if the nitrogen loses this electron from P3, it will become P2 configuration. And P3 is a half-filled configuration, that is a stable. So since the nitrogen is having a half-filled configuration, so in this case the nitrogen will try not to lose this electron, and due to that stability it requires more amount of energy compared to the expected. So here the expected value is here the expected value is much less than the amount of energy which is required because of this stable configuration. While in this case the P4 is not the stable configuration, and if P4 is not the stable configuration, then it will require as usual the amount of energy will be needed. So in the case of nitrogen and oxygen, the energy of the nitrogen should be low compared to the oxygen, but the thing is exactly opposite. The reason that the nitrogen is having stable configuration in its half-filled stable configuration in its ground state, while oxygen doesn't have any such type of stable configuration. So since it have stable, that's why it require more energy. Okay, now let's see from top to bottom what happens. Here I'm talking about the alkali metals. Lithium 520. From top to bottom, since the shells goes on increasing, so the attraction becomes weaker and hence less energy is required. 520, less and less. That means here from top to bottom continuously the energy required to remove the electron goes on decreasing. Okay, now for beryllium, let's see one more some exceptional thing. For beryllium, first for lithium. For lithium, the first ionization enthalpy for the lithium, it is 520, while the second ionization enthalpy for beryllium is 7298 kilojoules per mole. Similarly for beryllium, if I am writing, the first ionization enthalpy is 900, while the second ionization enthalpy is 1758 kilojoules. Now here the question arises that for lithium, the lithium which comes first and beryllium here, it's a first ionization enthalpy 520, this is 729, first ionization enthalpy of lithium is less than beryllium as it is expected because the beryllium comes on the right hand side. But when we talk about the second ionization enthalpy, exactly opposite thing we observe. Second ionization enthalpy of lithium is more while the beryllium is less. Why such thing is happening? Let's see the reason. Again, it is based on the electronic configuration. Lithium, the electronic configuration for lithium, atomic number is 3, 1s2, 2s1. Suppose the first I'm talking about the first ionization enthalpy. First ionization enthalpy means if you want to remove the first electron, then ultimately this electron will come outside. If this electron comes, so for removing this electron, how much energy is needed? 520 kilojoule. It will come outside easily. But after once this electron is out, The left configuration is 1s2, means 1s2, that means the first shell with the complete duplet. That means the configuration becomes like the configuration of a noble gas, that is helium. So once it's a configuration after losing one electron, its configuration of lithium will looks like a helium configuration. That means it get extra stability, completely filled the noble gas stability. And in that case, if you want to remove one more electron, second ionization enthalpy means I wanted to remove second electron. So once this electron is removed, the second electron will be removed from here. And what do you think, whether is it possible to remove this electron easily? Then answer is no. This electron will not come outside easily. The simple reason that is, after removing this electron, this is having stable duplet configuration. So in that case, if you want to remove this electron, then very high amount of energy is required to break its stability and then to remove the electron. And that's why the energy required is exceptionally high, that is 7298. But when I'm talking of in terms of for the beryllium atomic number is 4, 1s2, 2s2. 2s is having 2 electron and 1s is also having 2 electron. Let's suppose I wanted to remove the first electron from this. First electron means I will remove this electron. Here the energy required for removing the first electron is exceptionally high. The reason because it is having a s2 configuration. But once you remove the first electron after absorbing so much amount, we remove the first electron after producing so much amount of energy, then the configuration will changes to 2s1. This is the case after removing one electron. Then removal of the second electron will again easy, because 2s1 configuration is not the stable configuration. It's an unstable configuration already. So the removal of this electron will become easy, and that's why the less energy is needed, that is 1758. And after removing this electron, the configuration will changes to 1s2. Yes, now in the case of beryllium, if you want to remove the third electron means now the third electron will be removed from this 1s2 configuration. Again, the configuration is like helium, noble gas configuration. So if you want to remove this electron now, then it will not lose this electron easily, and that's why to remove this electron a very high amount of energy will be required. And here for beryllium it has been measured as 14,850. You can see the difference between the second ionization enthalpy and third ionization enthalpy, and such a large difference between second and third is only because of the stable configuration of this beryllium after losing 2 electron. That is, if you want to remove third electron, that means you have to break the stability, duplet stability of the beryllium. So this is about the ionization enthalpy and the factors which affect the ionization enthalpy, and how this value changes because of the electronic arrangement